Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the session on prediction engines. It's my pleasure and honor to host this session with three awesome speakers, Robin Hanson, Nicholas Lambert, and Sanmay Das. And I'm hosting this session on behalf of several Microsoft researchers who work on this area of prediction engines: Miro, Sebastian, David Rothschild, and Jen Wortman-Vaughan. I just wanted to set the stage and set some context. What do we mean by a prediction engine? Okay, let's break down this phrase into its parts. Prediction, first of all, prediction. At least for the purposes of this session, for the next three talks, by prediction I don't mean a categorical statement, Hillary Clinton will win the next election, that like a talking head or pundit may say it. What I mean is basically a probability. A statement of uncertainty, 27% chance that Hillary Clinton will win the next election. Something, after all, that reflects the true state of the world, right? No one knows for sure whether she will win or not. All we know is there's some chance. But along with a statement like that is a little bit of difficulty in evaluating it. So any statement like that on its own, you can't say whether it's right or wrong. Right? So even if you say there's a 70% chance Romney will win in North Dakota, say in the GOP primary, that particular prediction may be wrong, but you really need to evaluate those predictions in groups. So among these 10 predictions that we made before Super Tuesday, for all the Super Tuesday states for the GOP primary, among these 10 states, a total percent chance of 875% chance, so we expected to get about 9 out of 10 right, and that's about the ratio that we achieved. So what about the engine part? Prediction engine. The engine is the technology side of things. The reason why things are different today than they were 10, 20 years ago. It's the computational power, the new online world that's making these things easier. So the technology to collect predictions from experts from a crowd, the technology to formulate predictions from historical data using machine learning, using statistical modeling, the technology that's transforming the way we do polling. So for example, doing a standard random sample is still quite expensive, but doing a self-selected bias sample has become virtually free in the world of Microsoft, Facebook, Google, etc. Like one of the researchers, David Rothschild, thinks and works a lot on this topic. Taking things like prediction markets, which I'll talk more about in a minute, and improving the way that we can, the way that we run these things. And like a lot of these things, the devil is in the details. The user interface matters a lot. Again, technology is changing things. We no longer are restricted to calling people and asking a single multiple choice question. We can make a graphical interface. We can make it interactive. We can make it entertaining, make it engaging, and we can get a lot more information from people with platforms like Xbox, for example. And we can think about the incentives, both the sort of gaming incentives and also the monetary incentives. And once we have these predictions, we have to think about how to combine them, either through averaging or through machine learning, through online learning. We can think about how to handle combinatorial predictions or related predictions. So for example, a prediction about if someone predicts that Clinton will win both Ohio and Florida, that says something about her probability to win just Florida by itself. And once we have this sort of combinatorial explosion of predictions, we need good ways to browse and search through predictions. We need ways to explain predictions to the average consumer and help visualize those predictions. And all of this stuff is adapting as we speak, and we at Microsoft and among the speakers are engaged in constant experimentation and tinkering. And one of the things that we do a lot is think of a new idea, actually build that thing, open it up to new users, see what happens, and repeat. So ideally, the ideal prediction engine would predict, it would be general purpose. It could be used to predict, nearly anything, even things we don't know much about. It would be accurate. It would be real time. It would not only have the capability of predict nearly anything, but be able to do that affordably. And kind of a side goal is to get past the current state of affairs, which rewards people who are the most persuasive, people who are saying things with the most conviction, or people with the most power, or even people with the most computational power, the fastest computers. Get away from that and give credit where credit is due. So the extent that the engine is rewarding or giving reputation and credit, it should reward actual information and not these other factors. So one prediction mechanism that at least two of the three speakers will talk about, and if not ideal, at least it does have a lot of those properties, is a prediction market. So I'll define what that is, so the speakers don't have to. So this is, for example, take a random variable like will Clinton win the next election, turn it into a financial instrument that pays $1 if that happens, and nothing otherwise. So in 2016, after the election, that contract will be worth either exactly 1 or exactly 0. But today, we don't know how much that's worth. It's worth, basically, it's worth the expected value, or how much, whatever you think the probability of that event is. And different people will disagree on the probability of that event. Some people may buy, some people may sell. There could be millions of dollars traded on that security, but eventually we'll reach some sort of equilibrium price, at which point no one's willing to move the price further, and we can think of that as an estimate, a consensus estimate of the probability of that event. And you can trade that online on places like betting exchanges like Betfair, and it runs exactly like a continuous double auction, sort of like just like the stock market works. There's a bid queue, there's an ask queue, and it may look hard to interpret, but it's written in terms of European odds, but you can convert it back into probabilities. And what this is saying is basically, according to this market, she has between 27 and 30% chance of winning. And so this type of technology can allow us to predict, predict many things, even things we don't know much about, like, for example, Eurovision. One place to go that has like an aggregator is David Rothschild's blog, PredictWise. It collects together lots of these predictions from all around the web, from different markets, from different sources, and puts them in a format that's easy to digest. And this style of market has a good track record of empirical accuracy. So this is just one example, but there's a lot of examples. This is over several decades, predictions about football games. And it's the Vegas odds. It's the place where people are putting real money down on the line, which is getting the most accurate predictions. This type of technology is also real time. So here's an example where we were writing about the prediction markets during the GOP primary. And as a result, I was watching a lot more debates, Republican debates, than I recommend anyone to watch. But one of those debates, if you remember, there's one debate in particular where Rick Perry, he already had a few weak debate performances, but there's one particular debate where he couldn't remember the third of the three government agencies that he was going to cut, and he just couldn't remember. He finally just said, "Oops, I can't remember." And almost within hours, his probability of winning went from pretty small to basically negligible. Went from 8 down to 4. Another example of real time, so right before Super Tuesday, the markets were giving Romney an 80% chance to win Ohio. But actually, all the polls were favoring Santorum in Ohio. So what was happening? Romney had just won in Michigan the day before, and the market knows that all these states are highly correlated. So if Romney wins Michigan, he's likely to win Ohio, and the market can react almost immediately. The polls take a few days to catch up. Again, polls versus markets. If you remember the primary season, if you were just watching the polls, lots of different candidates had their time ahead. Rick Perry, Herman Cain, Gingrich, Santorum, and they kept swapping with Romney. Even at one point, believe it or not, Donald Trump was at the head of the Republican polls. So if you're just watching the polls, and this is the story the media wants to highlight, is that, well, Romney might lose. All these other people are ahead at various points. But actually, if you're looking at the market, it's a much more boring story throughout the primary. Really, Romney was favored almost the whole time, with the exception of at the beginning with Rick Perry coming in, and then a couple days at the end of 2011 where Gingrich and Romney were close to tied. So you can get lots of predictions like this on places like Betfair and other places. Pretty amazing. You can go get predictions about all types of political outcomes and other outcomes, but sort of by definition, there's only a polynomial number of those predictions, right? Because the way they all run is every single prediction is its own continuous double auction with its own database, its own order flow. What we worked on building is what you might call a combinatorial prediction market, or getting more towards this predict almost anything concept, where you can take an exponential explosion. So if you think of all 50 states as binary variables, now you can predict any Boolean function of those 50 variables. Like Romney will win Iowa, but Obama will still win the election. Or the same party will win both Michigan and Ohio. Or Obama will win between 6 and 8 states that begin with the letter M. Or there'll be some, after the election, there'll be some path of blue that goes, that connects all the way from Canada to Mexico. So you can make all these kinds of predictions, and from that you can get interesting correlations that help answer questions like how pivotal was Ohio really? Everyone's saying Ohio's pivotal, and everyone is saying all the money's flowing into Ohio, but we could actually show that, well, actually it's true. If Obama wins any of Ohio, Florida, or Virginia, he had a very, very high likelihood of going on to win the election, whereas Romney really needed to win all three. Or we also had some things which correlate, like if the jobs report in October, we could correlate between what the jobs report in October looked like and Romney's chances. So if the jobs report looks bad, Romney might win. And actually moving forward, and maybe Robin will talk about this, we'd like to get beyond the horse race of it, like who will win and why, and more towards like what is the outcome of the election. So if Romney wins, what will happen to unemployment? What will happen to war casualties? What will happen to tax rates? What will happen to health care, et cetera? And that's presumably the things we actually care about. The not the actual individual in the White House, but the policies that he or she puts forth. So we built that combinatorial prediction market. In theory, it allows you to create billions and billions of predictions, or actually, in this case, 18 quadrillion, for quote unquote for free. But in practice, there's a lot of questions about whether people can actually anything interesting can come out of people playing in such a vast space. So it was a fully working beta and field test that we ran with just a few hundred users, or about 700 users. And you can read about those details in the recent paper that we had in the ACM Electronic Commerce Conference. And this is kind of what it looked like. You could make those kinds of combinational predictions, like the same party will win both Ohio and Pennsylvania. And the amazing thing to me is, these few hundred traders are doing something quite interesting, just for fun, not for real money. They are able to do, even on a question like jobs numbers, do something intelligent. And so, for example, because of the combinatorial language, we don't just get the point estimate of the number of jobs created in September, but we can get an entire distribution. And you can see the blue line is how we initialized it, and our traders really did, they sort of narrowed the prediction and moved it to the left, and they ended up peaking right around the actual number. So we'll go on with now, like I said, I'm honored to host this session. We have some amazing speakers. I'll introduce them one at a time as we go. And these 3 speakers will cover, if not a representative sample of topics in prediction engines, a pretty wide spectrum of different topics in prediction engines, including getting information from an expert, getting information from crowds, including prediction markets, including scoring rules, including experimentation, including combinatorial prediction markets. So I'm excited to go forward, and I'll introduce the first speaker. The first speaker, and what we'll do is we'll try to have each speaker about 15 minutes. We'll try to have time for questions after each speaker, and then we'll try to save some time at the end for questions for all the speakers. So Sanmay, if you can come up. The first speaker is Sanmay Das. He's a professor at Washington University in St. Louis in the computer science department. He does work in machine learning and computational social science, and he won an NSF Career Award, and his degrees are from MIT and Harvard. So thank you, Sanmay.
Okay, sounds good. Okay, great. Thanks very much for the introduction, Dave. It's an honor for me to be here. So I'm going to be talking today. So actually, I'm not quite yet at WashU in St. Louis. I will be there in a month or two officially. I'm still technically a professor at Virginia Tech. And I'm going to be talking about work I did before this at RPI as well with several of my students and colleagues. And I'm grateful that Dave has set all of this up so well for me, and it's a pleasure to be giving this talk in front of many of the people whose work really excited me about this area. So just continuing on with this idea of what are prediction markets good for, I'd like to talk about them for a little bit and draw some analogies to financial markets and how we think about information flowing in these markets. So I'm going to talk about 2 different ends of the spectrum. One of these is the information aggregation end of the spectrum. And this is really, to my mind, one of the big benefits of prediction markets is suppose you're interested in getting a quantitative estimate of the answer to a question. So suppose you're interested in the probability that the global average temperature 10 years from now will be more than 0.2 Celsius higher than it is today. Okay? So you might have a lot of different people who have different opinions about this. So you might have people who are domain experts. You might have people who are policy experts. In this case, you might have Al Gore, who has strong beliefs about this issue. You might have people who are conspiracy theorists of a certain kind, or you might just have the average person sitting at home who's like, I have no idea why are you asking me this question, right? What you want to do is you want to come up with a number that you can meaningfully use as an estimate of the probability that this event will actually occur. So one of the things that prediction markets are really good for is essentially incentivizing people to put their money where their mouth is so that people can come in and affect the price and get it to move to actually give you something that you can use if you're going to be making decisions based on an actual probability that this event will occur. So this is the sort of information aggregation end of the spectrum, and it's something that financial markets, for example, are known to be very good at in terms of valuing what is a company worth, right? In the same way, prediction markets can be really good at figuring out what is the probability that an event will occur. There's another side of this, which I consider sort of the opposite end of the spectrum almost, but something else that prediction markets are also very good at, is this issue of information dissemination. So in this case, you have all of these people. They have all this evidence that's available to them, and they have their good faith opinions based on this evidence. But it's possible that they just don't have all the information that they need in order to come up with a good estimate, right? So it could be that all of these people have their own opinions about what the temperature is going to be, but Dr. Evil is sitting over there being like, ha, 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 I have this evil plan to focus lasers on the Earth and heat it up, right? So what happens now? Well, it's possible that Dr. Evil has a henchman who wants to profit off of this information. This henchman knows that the Earth is going to get much, much warmer because Dr. Evil is going to focus lasers on the Earth. So the prediction market incentivizes this person, Dr. Evil's henchman, to come in and basically trade based on the information available to him and drive the price towards sort of a correct estimate. So there's the information aggregation end of the spectrum, there's the information dissemination end of the spectrum. They're actually sort of, along the same scale. These aren't completely separate things, but these are two things that I want you to keep in mind as we go forward. Okay, so Dave has already set this up pretty well, but there's plenty of evidence now that prediction markets do a really good job at several of these information aggregation types of tasks. So, the classic example that they're well known to do well at is in election markets. So, the Iowa electronic markets, which operate in the U.S., and Intrade, which is now unfortunately shut down, Betfair, which Dave talked about, have all done a very good job of predicting big election outcomes. The Microsoft project on the combinatorial market for the 2012 elections did an impressive job of producing various forecasts about different types of combinatorial outcomes in that space. We know that prediction markets have been used and done a relatively good job at sales forecasts and so on in the corporate setting. And then there have been lab experiments that actually try to demonstrate the information aggregation properties, some of which Robin has been involved in. And it's pretty clear that most of our intuitions from financial markets carry over pretty well in this information aggregation setting. There's been somewhat less work at this dissemination end of the spectrum, as I like to think of it. But there are a couple of examples where it's worked pretty well. So I think one of the famous examples was that Microsoft was running internal prediction markets, and the moment that these markets went live, it became clear that there was a product that was scheduled to be released that many people thought would be released on time that was actually not going to be released on time. So that was an example where the existence of the prediction market incentivized people who had the information to come and reveal it, and therefore better information became public than would have been public otherwise. Another example that I thought was really neat was the Gates-Hillman prediction market, which was run by Abe Othman and Thomas Sandholm at CMU, where they were basically running a market on when will the new computer science building open. And there were various interesting findings from that, including things like there was one person who was a really active participant in this market who became good friends with the building supervisor over there and had the building supervisor's cell phone number and used to get phone calls from the building supervisor whenever there was any big information happening over there, and then trade based on that information in the market. Another example that I'm going to talk about is some recent work that we've been doing that will be presented at AAAI actually tomorrow on instructor rating markets, where we've been running prediction markets in which we get students who are taking classes to actually predict what evaluation will their instructor receive, as a way of both providing dynamic feedback to instructors on the progress of their classes and what's going well and what's not going well, as well as to actually perform a field experiment in markets where manipulation is possible, because people are actually affecting the very outcomes that they're trading on, because people who are trading are also the people who are rating their professors. So what I want to talk about briefly today in the next 10 minutes or so is two different big research questions that I see as very important questions for the future of this field. The first of these is, what's the right way to design these markets? So I'll talk mostly about markets that are either binary, that is 0-1, or continuous outcome markets, where, as Dave mentioned, the standard approach is to use continuous double auctions. But there are many other options for how to design these markets, and I'm going to talk a little bit about the option of including a market maker who is a liquidity provider to incentivize people to come and trade in these markets, and talk about what the possibilities are. And I'll talk a little bit about comparing two different market makers, the logarithmic market scoring rule, which is due to Robin and has been greatly popularized in the AI community by the work of Dave Pennock and Yiling Chen and others. So I'm going to talk a little bit about what are the different trade-offs that you make when you structure these markets in different ways. There's also, I should point out, a whole host of interesting questions that I won't touch on, which is, what's the right way to design combinatorial or interval markets? And I think others may speak about this as well. But I think that one of the really cool areas in which computer science can be very helpful is in thinking about the interface between the front end and the back end. That is, what's the user experience like? What is the set of levers available to them to actually convey their information to the market? And how does that interact with the pricing engine at the back end? The second big set of questions, I think, for prediction markets research is the question of whether manipulation is a problem or not. So there have been lab experiments that suggest that, price manipulation as such need not be a problem. But, there was this somewhat famous failure of the policy analysis markets, which somewhat unfortunately got branded as betting on terrorism in the public media. But let's posit for a moment that people don't want markets in which you can go out there and you can bet on, okay, will there be a terrorist event in Seattle or in New York City, during the next week or so. Let's just, assume that that's not possible. That's not something that the public will accept. There may be moral issues and so on. At the same time, it's very clear that election markets, for example, have been very successful, and there's no issue with that, right? But these things fall along a spectrum, right? There's somewhere in between there where there are options of sort of how manipulable these markets are, how much insider information there is in these markets. And one thing that I think is going to be really important to determine in the future is, where does the line lie? What are the kinds of markets that we can successfully run, and what are the limits of manipulability in these kinds of situations, and when should we be concerned about it, and when should we not be concerned about it? So let me just dive into a couple of things. So the first question that I'm going to talk about is market making. So the standard design for most prediction markets is to run these continuous double auctions, which have typically been used in financial markets as well. The problem with that is that these markets can often end up being thin markets. That is, not a lot of people trading in them. And the famous saying is, liquidity begets liquidity. When people come in and they trade in markets, they create liquidity, which encourages other people to come and trade, therefore creating more liquidity, right? If you don't have people coming in and trading, then there may be people with information out there that they want to share, but they're not willing to come in and trade in that market because of the various risks that they would have to hold in order to do so. So one common solution to this is to use a market maker who is an agent who is specifically designated to provide liquidity in these markets. And the logarithmic market scoring rule has emerged as pretty much the de facto standard for market making in prediction markets. It's got a lot of nice properties. For example, it's got a loss bound that says that it can't lose more than a certain amount of money. It's nicely extensible to combinatorial markets and so on. However, if we're actually going to eventually be running real money markets and these things scale up, then there are some problems associated with this as well, which is that in general, if it's incorporating information, it will typically make losses, and it can be sensitive to a particular parameter, and choosing how to set that parameter can be difficult. There have been some extensions of this work, but one thing that we've been working on is to take a different approach to market making. And we've designed a Bayesian market maker that learns from the information content of trades. The advantage of our market maker is that it's not necessarily loss-making. The disadvantage is that potentially, there's no loss bound, so it's potentially capable of making a lot of loss. However, it can also provide pretty intuitive market properties that are the kinds of properties that we want. For example, having higher spreads during times of uncertainty and lower spreads during times of more stability in the market. The question becomes, how do we actually compare these market makers? So there's many different ways of doing this. And what I really advocate is an all-of-the-above approach, which is that I think that we should take every option available to us. So this includes doing things like lab experiments, which can be very well controlled, and therefore you know exactly what you're getting. But at the same time, they can be difficult to scale because they're quite expensive, both in terms of the time to run them, the availability of human subjects, and so on and so forth. Another great option is to run field experiments or to talk about experiences with deployments, as folks at Microsoft and other places have been doing, and as I'll hopefully talk for a couple of minutes about in terms of our instructor rating markets, which is to actually say, okay, we're going to run these markets in the wild, maybe get a few hundred people to participate. These are typically play money markets, but they provide a different kind of experience in which people have more time to interact with the market and to learn about it, and therefore we can learn new things. And the third kind of way of comparing them is to really run experiments in which you have a bunch of trading agents who are participating, or run tournaments. So I know that many economists get scared when you start talking about agent-based modeling, but a couple of things to keep in mind over here. One is that you can run a lot more tests in this manner, and while it's important to be careful about how you interpret the results, this can be really great for debugging, because you can end up seeing many different properties of the market by varying the compositions of different types of traders in the population. Just to give you a quick example, so we've run all of these kinds of experiments, but so we run some trading agent experiments where we gave agents access to slowly improving information on the true probability of an event through basically repeated coin flips. And we allowed them to use different strategies in this. So we had traders that would just trade based on these fundamentals. We had traders who were so-called rational expectations or learning traders who would use both their own information and the market price. And we employed various agents that were using different trading strategies from the technical trading literature, for example, momentum traders. And then we varied the proportions of this in the population. And so we tried to compare our market maker, the Bayesian market maker, with the logarithmic market scoring rule across a broad range of settings. And what we've got over here, so I'm just going to briefly go through this. What we were interested in comparing is, what is the average profit that the market maker makes or the loss that it takes? What's the spread, which is a measure of the liquidity that the market maker is providing to the market? And what is the root mean squared deviation that is a measure of the accuracy of how good is the price in comparing with the fundamental value? And in these experiments, we can see that across a pretty broad range of settings, for approximately the same amount of liquidity being provided, the Bayesian market maker has the advantage over LMSR of potentially being able to provide more price accuracy without needing as much subsidy in order to run the market. The caveat to this, of course, is that we don't have a loss bound, so it's possible in catastrophic cases for the Bayesian market maker to actually lose more money than the LMSR's loss bound would allow it to. But basically the point over here is that you can run a lot of different specifications and you can learn a lot about the behaviors of these kinds of market structures by using trading agent experiments as one of a set of options, including lab experiments and field experiments with deployment. Now I'm very quickly going to go through my instructor rating markets experiment, where analogous to election markets, what we wanted to do in this case was run markets where instructors who were teaching the class could receive dynamic feedback on the progress of their class by allowing students who were taking that class to actually trade on what evaluations the instructors would receive. So what we did was we ran markets for 10 different classes at RPI. Each course had a security that liquidates between 0 and 100, with all orders going through a market-making algorithm. So now students at RPI could trade in any of these markets, but they were only allowed to rate instructors for the classes that they were taking. We ran 5 2-week rating periods, and in each rating period, everyone's account started with an initial allotment of fake money or shares. At the end of the 2 weeks, students in the class rated their instructor, and each market would liquidate based on the average rating received by the instructor, which is a number between 0 and 100. And we gave people prizes that were essentially lottery-based, but based on sort of how much money they had won in the prediction markets. And the prizes were like iPod Nanos and Apple TVs. So the big question that we were thinking about is, are these markets going to be manipulated? Well, the short answer is we found very little evidence of any manipulation in this case. So for one, is there price manipulation? And basically the answer is no. Prices incorporate new information. And we found in all our tests that the market prices were reflective of the actual ratings that the instructors would receive at the end of that 2-week period. Who was providing this information? Well, we ran a test to try and figure out if it was students who were in the class that they were taking who were providing the new information or not. I won't go into details of the test, but basically we just looked at trades that occurred between the last liquidation price for that instructor and the next liquidation price, and tried to see if the trade moved the price in the correct direction or not. And we found that people who were in the class would trade more often than not in the correct direction, therefore moving the price towards the future liquidation, and people who were not in the class would trade towards the past liquidation value. So it was students who were in the class who were providing the information. The final question becomes, okay, but what if the whole thing is a big fake, right? This is a fake world we're creating. Everyone could just agree, hey, we're going to rate the instructor high and bet all our money on it, and then we're all going to make a lot of money. Turns out that this did not happen, because the correlation between the ratings that instructors received in this case were very high with the official institute evaluations, which were completely unrelated to our markets that we did at the end of the semester. So just in closing, the takeaways that I want you to go home with from this talk are, there's a ton of exciting applications of prediction markets, ranging from things that we care about as professors, like instructor ratings, to important policy questions, exciting questions about combinatorial outcomes. But in order to actually get this to work, there's some really interesting research questions to dive into. We have to design these markets right to get them to work. The devil is in the details. So there's questions about, should we set these markets up with a market maker? Interesting questions at the interface of market design and user interface design. And we also need to think very carefully about manipulation. We shouldn't throw the baby out with the bathwater. Just because manipulation is possible doesn't mean that the market won't be useful and that it won't convey to us information that we can use to make better decisions in the future. So, thank you for your attention.
Maybe one question, and Robin can come up. One or two quick questions. Any questions?
I just wondered if you looked at gamification in any way and using game theory integrated with prediction markets and how that might influence your experiment.
So the question was, have we looked at gamification and essentially using game theory in, integrated with these markets in some ways? So yeah, I mean, we've thought about a lot of these issues as it goes along. So one issue that often arises, especially in the context of the instructor rating markets, is how do the particular incentives that we set up interact with the outcomes that we see? And we're using these rank-based incentives. It's kind of like the NBA draft lottery. That is, how much you get affects the probability that you're going to win one of the prizes. So that obviously can lead to different behaviors than just running a market where you get proportional outcomes. We thought it made sense for this case, and I don't think it affected our results very much, but I think that that's something that's very important to think about anytime that you're designing one of these markets. That is, how does the particular structure of incentives you've set up interact with the behavior that people are exhibiting in that market? Thanks. Thank you.
Okay, thank you, Samir. So the next speaker is Robin Hanson. He's an economist and professor at George Mason University. In many ways, he's the sort of father of prediction markets, or pioneer of prediction markets. He's principal architect of some of the first internal corporate prediction markets and some of the first web markets, and also has done a lot of innovations on combinatorial and conditional prediction markets, and also manipulation in prediction markets. So thanks, Robin.
Thank you. Some of the work I'm presenting is joint with these colleagues of mine on the Dagger project, which I'll tell you about in a moment. These are some screenshots from the Dagger project. So on the left hand, it's not that pretty, but it's what we could do. On the left hand side, we have a long list of topics in world affairs. If you pick one of those topics, like number 359, it'll tell you about that this is a question on, back in 2012, whether Israel would invade the Gaza Strip. At the moment, at that time, there was a 20% consensus in the system. That was the best estimate of the system of the chance of that event happening. And you, as a user of the system, were tasked with browsing these estimates and finding one you thought was wrong. And if you think it's wrong, changing it to something you think is better. So you might pick this and edit it to be 16. And then what it would do then, it would tell you that if this event turns out to be true, you will gain so many points. And if it turns out to be false, you'll lose points. And in general, you are betting that the estimates you're providing are an improvement in information. And so you end up with a relative stake. And in the upper right-hand corner, you see your expected score. On average, what your score will be. And your task is to try to increase your score and to therefore contribute more information to the system. So you approve the edit, and after your edit, the system shows to everyone else the edit you just made. That's the current best estimate. If they don't like it, they can change it again. So this is an edit-based interface, a way to do prediction markets where each person, there's always a consensus on everything. You go in and find the things you think are wrong, and you change them. This system was special and different because this is a combinatorial prediction market, as Dave was talking about. So in this case, you can take any of these other questions on the right-hand side, you can pick one, and you can assume it. So you can assume that at least one Hamas rocket will blow up in the Jerusalem city limits between a certain date, and you might think that event would be predictive of the event in question here on the right-hand side. And so you could go make an assumption, and now if you edited that number on the right-hand side, you're editing a conditional estimate. This is the conditional probability of that event given the assumption you make. And in this system, we could make several assumptions on the left-hand side. So the interface we're trying to offer is you can go in and edit a joint distribution over the set of possibilities. And at any one time, there's a consensus, and you can change it, and you have the incentive to change the consensus toward the truth so that you will, on average, make profits that way. So this is the Dagger system that we worked on together. Now, the Dagger system was on foreign affair events. It's over now. It ran for almost 2 years. We had roughly 100 claims at a time that were up there that you could edit. And we had thousands of users, but typically only 300 per month actually doing something. And we paid our users, we had a fund of money, we paid them for their participation. We wanted to be able to pay them for performance, that is, ones who did better get paid more. We were not allowed to do that because apparently because we're developing something to be used in the government later, they never pay people for performance there later, so we can't pay people for performance here. That was the argument. So we are now moving to a new system that we're beginning and we haven't yet fielded, but to go live in a few months. And this is going to be called SciCast, and this will be on science and technology questions. So we want to solicit people's participation to help us develop good questions about the progress in science and technology. And we are tasked with increasing our numbers by a factor of 10 in terms of having 10 times as many claims live at any one time, 10 times as many users active doing things. And no, we can't pay people anything now, because apparently this gamification meme has gotten around, and there's no need ever to pay anybody for doing useful things because you can just make things fun, and then they'll do all your things for free. Thanks. So I'm going to tell you now about some of the technology behind Dagger and some of the technology we're going to develop for SciCast. There's lots of wonderful things you can do with prediction markets. I'm, in general, very excited about the general potential, although it gets frustrating because it's hard to get people to actually use them. But here's at least a place where we're doing it. But this is a computer science audience, so here I'm going to tell you about computer science like tech. So some people have already discussed the logarithmic market scoring rule. So the idea is that ordinary markets like the stock market have a performance problem. When you have lots of people trading on a small number of claims, they work great. But if you try to get lots of estimates out of a few people, they work lousy because you end up with this thin market problem. There's an old tech called the scoring rule, proper scoring rule, many of you may have heard of. It's a way to just ask a person lots of questions, and you can do that, and it works fine. But then when you have lots of people answering the same question, there's always been a problem how to combine that. This market scoring rule is something that does a nice interpolation. It becomes a scoring rule or an ordinary market, depending on the circumstances. And it is basically a proper scoring rule that's shared. So you can think of a line of people using a proper scoring rule. And the rule is that each person gets to use the proper scoring rule if they just pay off the last guy in line. So they get the difference, so they have the same standard incentives. But that difference means that it ends up being equivalent to a market maker in a market. A shared proper scoring rule is equivalent to a market maker, and there's a direct relationship there. And it turns out also that there's a nice uniqueness property about this sort of mechanism in terms of combinatorics. If you make a conditional edit, the probability of A given B, that edit doesn't change the probability of B. It only changes the conditional probability only if you have this particular logarithmic market scoring rule form. The general task, though, as a computer scientist here is there's going to be this probability distribution. You have to let people edit the probability distribution. You have to pay to represent and store that. But in addition, you have to have a data structure that represents their assets. How much they will get or lose in any particular state. There's a simple formula that represents the relationship between the edit they make and their assets. And it's a very nice and elegant thing to have. Also, you tend to want to produce an expected score, averaging over all the states. What's their average performance? And you sometimes want to do that conditional, as I'll say. The problem is the generic way to do this, if we've got way too many states, is just not feasible. So how do we handle a combinatorial space of assets and states? So I want to frame this as a set of problems and solutions. The generic idea is that simple prediction markets work fine, but they only give you a small number of topics. What we want to be able to do is elaborate this full combinatorial space. But how do we represent that? How do we have a limited representation of the combinatorial space? There's a well-known technology of Bayesian or Markov networks we're going to apply. There's very standard ways to create Bayesian and Markov networks with a limited representation to express a joint distribution over a large space. But the problem is those algorithms and methods were developed for probabilities, and they didn't even think about assets. How to store and represent a combinatorial representation of assets and how to update that in the response to these sorts of changes. So we're going to find a way to use a variation on Bayesian networks to also store and update the assets so that we can have a full combinatorial prediction market based on Bayesian networks. There are many ways to do combinatorics. I like David's approach in many ways. The emphasis here is we stayed for a while at least on Bayesian networks that we can compute exactly. So there are never any errors other than round-off errors. And so we never have to worry about being a money pump where users can anticipate our errors and then take us to the cleaners because we're making mistakes in calculating the prices. Here we never have to make mistakes in calculating the prices. So within that realm, how far could we get? So here's the problem of what we're trying to do in the abstract. Users browse a set of estimates. They make assumptions if they like, and they see various conditional estimates. And at some point, they find a particular one they want to focus on. And so at that point, the system has to be able to compute conditional estimates. So that's the first item there, the probability of a target variable that they're focused on, conditional on the assumptions they've made. And we have to be able to compute that. Next, they're thinking about editing this number. And it's good to give them some context of their current assets in relation to the thing they're thinking of editing, i.e., are they on net long or short? Do they at the moment stand to gain or lose? Depending on how this resolves, that will inform their choice. If they're already really long, maybe they don't mind as much going short because they're backing off on previous trades. If they want to go long more, they're sort of going more all in here. Maybe that's more risky. And in addition, what we'd like to be able to do is tell you, this is the current number. Given your current resources, this is as far as you could move it. We could give you the limits, or we could have you try something and tell you, sorry, no, that doesn't work. So the user then commits. They say, I make this edit in the range. Then we have to update our representation of the probability distribution to reflect that. We have to update our representation of their assets to reflect that so that we're ready to start over again. And periodically, users like to see how they're doing in terms of an expected score of their overall portfolio. And so we want to be able to calculate that as well. So these are our generic combinatorial edit-based system needs. This is what we need to compute. Want to highlight one issue, which is one simple way of doing this is with respect to each edit, it's easy to figure out what a pile of assets looks like that edit creates. And you could just typically take cache, make little piles of assets, and leave them with a big pile of stuff. The problem is they quickly run out of cache, and then we don't necessarily know how to take this pile of things they bought and use it to support new trades. What we want is an integrated data structure that makes it easy to calculate for any given new trade how to use all the things they bought before in order to support that new trade. So this is an illustration here. You could have made a bet on B given A1, B given A2, etc. And on the right-hand side, we show you that you could have taken X dollars of cash and created the following assets with that. And if you just had a simple system that did it that way, you'd end up with this pile of stuff on the right, but you wouldn't necessarily know how to take the pile of stuff on the right and use it to support new trades. Particularly, you might not notice that the trades on the right-hand side, the far right-hand column, that just adds up to cash. And a smart system would know that you had lots of cash to support new trades, and a dumb system wouldn't realize that. So that's part of the computational challenge here, is to have a system that knows how to figure out, given the trades you've made before, what that represents in order to support new trades. So as I said, we're using Bayesian Markov networks, which should be familiar to lots of you. A key working assumption of Bayesian Markov networks is that you have a product representation of the probability distribution. The probability of any one state is a product over what's called cliques and separators, which are these clumps of variables. And it turns out with the function that the logarithmic Markov scoring rule, we can make a simple transformation of the assets, a logarithmic transformation, exponential one, so that the assets also satisfy a product rule. So that means we can use the same mechanisms that use the product rule to represent and update probabilities to represent and update the assets. And that's our key trick. So that we can then use exact updating of probabilities, exact calculation of minimum probabilities. We translate that to exact calculation of assets and minimum assets to support trades. And also, simple variation allows us to do expected assets. That also tends up to be, we do a sum over each of these cliques, and we get expected assets. So we did a test before we went live, showing some scaling of these variables. And in fact, as usual with a Bayesian network, things are exponential in the tree width, but otherwise they're nice and linear in the number of variables that we have in the system. So in this test, we went up to 1,000 variables. In our running system, we typically had 100. And we typically had, say, a tree width of 5 or so it was actually quite feasible. So basically, I've showed you that with these, this basic set of approaches, we were able to achieve all these computational purposes. And ta-da. But of course, it's ta-da with respect to a set of constraining assumptions. And now we're asked to go beyond that. So again, we're asked to have a lot more claims. So that's more challenging computationally. We're asked to allow a much bigger tree width, not to constrain it to be a tree. Ouch. We decided that because it's really hard to actually do the expected value calculation, we'll back off and show people min-asset calculations for their long and short, which is often what they mainly care about, and that's a lot easier to compute. Whew. But another constraining assumption we had here is you're only able to make local edits in the tree. That is, all the variables that you were assuming and having as your target had to all be within the same clique, because that didn't violate the conditional independence assumptions of the network structure itself. So if you want to allow people to pick any variable anywhere and then edit any other variable anywhere else, then the question is, are they making a direct connection? Are they trying to change the network structure? Or are they accepting the rest of the network structure and trying to make an indirect set of things within the network to make that connection? We're also going to try to be more expressive about the kinds of values we can do. So because we're challenged to come up with thousands of variables, I had this clever idea. I say, OK, let's say we're betting on who's going to win the Nobel Prize in physics. We can think of that as a big abstraction category hierarchy with all these leaves, maybe thousands or tens of thousands of leaves about where the topic will end up being a winner. And isn't that like tens of thousands of questions? So therefore, we plan to have abstraction hierarchies like this that we can import and bet on major events, the end of the year, best innovation of the year, Nobel Prize, things like that, and be able to let people bet on where in the hierarchy this will end up. So they can start, say, at the top and just say in which category they think it is, or they can dive down if they have stronger opinions and edit lower levels of the tree and talk about this particular research project versus that one. So that's a way in which we can have thousands of variables and questions in essence with a relatively small structuring cost. Another thing we plan to do is that with this logarithmic marking scoring rule mechanism, there's actually a simple transformation that lets us present to the user piecewise linear asset functions that they can edit and or piecewise exponential probability distributions. And so, in fact, we just, behind the scenes, there's just a small number of, this is as if it were a small number of discrete values. But we can show it to the user as these piecewise linear functions. So now you can say, geez, I want to bet, I don't want to be so negative on 2030. Maybe I'll move that part of the curve up in terms of the line, and we'll move to another piecewise linear asset number. Or you could pick one of those points in the piecewise exponential curve and move it up or down, and you would be, in essence, editing that. And we know exactly how to do that in order to support it. And it's not very hard computationally. So, of course, one of the problems is betting on whether something will happen in 2030 or 2040 doesn't give a lot of activity for our users. But what will happen in the Nobel Prize or the New York Times Best of the Year is a lot more engaging to people because it'll happen sooner. So we'll, in the market, try to have both kinds of things. Long-term things that are of more fundamental interest and shorter-term things for activity and interest and to meet our number of questions mark. I think that's what I'll end with now and open it for questions. If your hand is up, I can't see it.
Questions for Robin?
It's Robbie.
Hi, Ravi Pandya, Microsoft Research. So I have a question. To what extent did you get a sense of how people understood the implications of making conditional probability assumptions? Like how consistent was that, or were they? Because there are a lot of known cognitive biases around that kind of thing.
We didn't get very much conditional editing. So the data on that is sparse. We had some lab experiments where there was more of that. In general, users of these systems can be best modeled as relatively noisy. It's the sum total of a lot of their actions together that produces something reliable and impressive, but you shouldn't trust anyone at it too much. Most people self-selected out. They didn't make conditional edits, so that gives me more confidence in those who did. They actually chose to do it. The conditional edits did in fact add information on average. So the markets were more informed because of the conditional edits.
Are the basic network structure learned or parameters are learned or manually specified?
We manually created the network structure, and we weren't too happy with having to do that, but at least we could allow people to make combinatorial edits. We would like in the next system to allow users to make more suggestions about the network structure, but we have a very basic trade-off in that we need to have a structure because that's the only way we can manage our computation, and it has to be limited, and so we can't allow everybody to edit everything. So we have to have some caution or reluctance. And in general, if we add some kinds of complexity somewhere, we'll have to take it away somewhere else. And so we have to decide what our rule for taking complexity away in order to keep a bound on that. So I have some elegant theoretical ideas which would work great if people were all abstract theorists. But we have much more concerns about how to do this with real people and their typical noisiness. So we expect we will have some combination of letting them make an edit and then saying, that doesn't represent our current network structure. Do you really mean to suggest changing the network structure, or were you just trying to say that the net effect of everything is this number, and try to push people to be more forceful if saying, no, I really mean your structure is wrong.
Any more questions?